That was record.
Question. We talked about this notation last time.
Yeah. So I don't put this out.
So it's like you were confused because this capital A is set, it's not just one thing. Look at this example, I think it'll kind of explain it. Suppose I say consists of these three little things, A, B, and C. When I use this notation right here, what that means is that's just this new set, that's three elements. It's X inverse AX, X inverse BX, and that's what's meant by that there. Well, let's begin. In our discussion of subgroups, let's let B, G, H be homomorphic. So I'm gonna find a couple of very important groups related to this homomorphism. One, the kernel of phi, which is a set of G and G, such that phi of G the identity of H. This is a very, very important subgroup actually. This is the set of everything in G that goes to the identity in H. You saw something like this in linear algebra. Do you remember when in linear algebra when you looked at the kernel of a linear transformation? Does that ring a bell to you all? Finding the kernel or whatever?
Yeah, I think so, like, what's the identity function of all?
That's exactly what this is in terms of group, right?
That goes to
The
zero.
kernel of a linear transformation was everything that was every vector that went to the zero vector, right? And that's exactly what's going on here. It's every G is playing the role of vector. It goes to the identity over here.
I've learned that on my own, like, maybe that's right for my own.
This is called the image of phi. The kernel of phi is a subgroup of G. The image of phi, that's everything, that's every possible image of G is a subgroup of H. So let's prove that these are in fact subgroups, because these are both very important, especially the kernel. Number one, by the way, can somebody name something that for sure is always in the kernel?
The identity elements, right?
Okay. So okay, the kernel phi is not empty, so I'm going to use the subgroup criteria. So let X and Y both be the kernel phi. That means phi of X goes to the identity and phi of Y goes to that. So if you look at phi of X, Y inverse, this is phi of X, phi of Y inverse. Because phi is an homomorphism. Can anybody think of some way that I can massage this one? It's another way to write phi of Y inverse. Right, that's one of our properties of homomorphism from last time. Phi of X is the identity of H. Phi of Y is the identity of H. So it's its inverse. So X, Y inverse is in the kernel phi. So kernel phi in G. So any questions on that? Yes.
With the, I forgot to work with the test, but how does just showing that? Like, why don't we have to assume, how is just showing that it's in the kernel of phi enough to say that's a subgroup of G, because I'm not seeing the connection to G, if that makes sense.
Because kernel phi is a subset of G, and
Okay,
it's not in.
okay,
And so all you have to do with subgroup criteria is if you take two elements that are in the kernel phi, it's a subset of G. If you can
Oh.
prove that X, Y inverse is in there, it's a subgroup.
if it's a subset of G.
Yes.
Okay, okay.
Number two. Uh. Okay, so the image of phi is not empty either. Because certainly if nothing else, we've got the identity of H in it. So I'm gonna do the subgroup criteria here. What does this mean? This means there exists S and T and G such that phi of S of X and phi of T is Y. Let me also point out that this last one means that phi of T inverse is Y inverse. It's taking the inverse of both of these. And this is the same thing as phi of T inverse. Now, note ST inverse is equal to phi of sorry, the end. Note X, Y inverse. There we go. This is phi of S, and that is phi of T inverse, which is phi of ST inverse. X, Y inverse, it's an image phi. So image of phi is a certain okay, any questions? Here's something I'm gonna leave mostly for exercise, although I am gonna prove, I think first. No, I'll talk way through a little bit here. I will call spot. 3.9. That B G to H B A B homomorphic. Number one, the normalizer from G kernel of B is equal to yes. So
Yeah, I did.
so two. Phi is onto if and only if the image of phi is flat. There's no real news here. This is true back from the 3190 days. This is true. This doesn't really have anything to do with groups as much as it does with sets. This is what it means to be onto. It means the codomain is covered. Here's the interesting part. And you probably saw something like this in linear algebra. So here's a linear. Let's see if anybody remembers this linear algebra. Suppose you have a linear transformation from a vector space V to a vector space W. Can anybody tell me how you can tell that linear transformation is 1-to-1? Yes,
Isn't the. Null space, the null space kernel is.
that's right. Trivial. Only zero button. Y'all remember that? So if you have a linear transformation from V to W, it's 1-to-1 if only if the null space is just a zero band. Right? There's an exact analog. This is the exact thing, Couched and Lang's group. Let me kind of sketch a little bit of this. And so it's exercise. Well, sure. We're called normalized from G of A. Set of G, B such that G. Actually, I think I complicated on the other side, but it doesn't matter. As long as you stick to what you pick. So I'll do it the way I'm here. So the normalizer in G of the kernel of phi is always contained in P by definition. Because by definition, this thing is a subset of the set. Why is this the other way true? Let G be an arbitrary element of G. You want to show yes,
So even like for other containment, like what do you say there?
you need to show that G is contained in this.
Oh,
Right? So you need to show every element of G is in normalized kernel. So we need to show that this happens. Any ideas on how to do? Well, this is a set, really. Right, because the kernel is a set, and this is a set. So how do you show two sets are equal? You can show containment both ways, right? So let alpha be convert kernel. Okay. So this is a big set. So alpha is equal to G inverse C G sum Z and kernel. That's what it means to live in this set. It's just well, G inverse some in kernel. That's what it means to live. Right. Now apply phi to this. Everybody agree with that? What is phi of Z? It's it is the identity because Z is in the kernel of phi, right? So this is the identity, right? So this is like an accordion. Squeeze this together now. Agreed. Well, we're not done because Goes to 4 and 12, sees if we can do this further. So. Uh. So that shows that G inverse kernel of the G is contained. Everybody okay with that? How about the other? Now suppose. So it means that D and C is yes. Yeah.
Or two, is that? Or what's the word after the?
Oh, image feed.
Thank you.
Okay. So let's check this out. Let's see, we don't want to do and G inverse. So let's look at this. Notice that this is an element G. Because G is in G is in C. Notice that P of G C G inverse. B of G B of C B of the inverse, and this is almost like the previous one. This is the identity. This is B of G inverse. Almost like this, except the G's and G inverse are in the other order. Great. So what conclusion can we come to? Yes,
Does it have to do with, you said one is always in the normalizer, or that the identity is always in the normalizer, so that's not like we're broken down.
no, so what we've shown here is. That's what we've shown, right?
Okay.
So. Now, this means that CG inverse equals G inverse alpha. Right, I hit that on the footer side. It's the right side by G inverse. Now, give it the left on D. So Z is in G inverse. Kernel of B. And that's the other thing. So we've shown that kernel of B is contained in G inverse kernel of B. So I've got this containment, I've got that containment, so they're equal. Thanks. Any questions on that? I want to look at 3 because it's very important, and you'll thank me later because it's much easier. It cuts a lot of work out just to verify that something is 1 to 1. And this is why it works, and this was, I mean, if they ever proved anything for you when you're algebra, you see essentially what I'm doing here. Three. Uh, and so. At kernel P. So we have Bx, is the identity of A, which is P when Q. This is a fact we've already established. We know that the identity of G goes to the identity of H. What can we conclude from this? About phi? Well, since phi is 1 to 1, it must be the case that what? Px equals phi of 1t. Since it's 1 to 1.
I mean, they only change that element.
So what we've shown is anything in the kernel has to be 1. Clearly one's in the kernel, so kernel of phi is precisely equal to just the set. Let's run it in reverse. Suppose kernel of phi is equal to identity.
We're going the other direction now.
Yeah. Suppose the kernel of phi consists only of the identity, and suppose phi of x equals phi of y. It is our burden to show that x and y are the same. Right? How might I do this?
Jump start.
Yeah.
The inverse of both, P of Y inverse on both sides.
Good idea. Good. How can I massage this? Right, bring that inverse into the y. And now use the homomorphism problem squeezes together. So this means that xy inverse is in kernel of phi, which is equal to g. Xy inverse is the identity of g, so x equals y. And so d is 1. Okay, any questions? Okay. We're gonna do something, I think, exciting now. So this is the first kind of little baby step to doing, it's kind of a small version of a kind of sophisticated problem that you might want to attack in algebra, group theory in particular. Now, I don't call this. We were going to classify also. Let me give you kind of a trailer for this. Yeah. How many groups of order 6 can y'all think of? How many have we seen? They're sort of different. You did the hard one first, right? D3, S3, And it turns out those two are the same, right? The dihedral group built on the triangle turns out to be the symmetric group. That is the largest n, namely 3, for which that is true. All right. There's another group of order 6 that we've seen that's qualitatively different.
C sub 6.
Z sub 6, right? The first examples were non-abelian, and this one's abelian, right? Are those the only groups of order 6? It turns out that isomorphism, yes. How many groups of order 10 are there? How many groups of order 12? How many groups of order 16? There's 14 different order 16. All right, and the powers primes get out of hand very quickly. We would like to list, maybe I want to know what all groups of order P are. Turns out where P is prime. Turns out there's only one of them. Yes.
So for order, going back to order 6, you said 3, right? But you said 2 of them were the same. Yes, okay. 2 of them were the same, okay.
So here we're going to classify cyclic groups. Now, I'm going to tell you what a cyclic group is too, but do you remember how we talked about if you have a generating set? So if I generate a group by X, Y, and Z, it's every word you can make with X, Y, and Z, and their inverses, X inverse, Y inverse, Z inverse, and there might be some relations, right? Like the dihedral group, we had R and S. It's all the words you can make with R, S, R inverse, and S inverse. But you also had some extra things. S squared is the identity. So every time you see 2 S's in a row, you can erase it. It's gone. R to the N, if you see N R's in a row, it's the identity. A cyclic group is a group that's just generated by a single element. Cyclic. Yeah. G generated by a single S. That means everything in this group is a power of X. Anybody give me an example of a cyclic group?
Oh yeah, the group generated by X and Y, or like just generated by X.
X and Y are sets.
Just X, like a group generated just by X.
Right, but that's a definition. Can you give me like something you've seen?
Powers 2.
Is that a group? So define what you mean by powers of 2.
Like the exponents like 2, 4, 8, 16, 32.
What's the identity there?
Well, I was gonna say the identity is 0, it's just 1, you know?
Right, but if you add 2 powers of 2, it's not the power of 2, is it?
Yeah.
2 plus 8 is 10.
Or I use multiplication instead.
Now you gotta have negative powers.
Oh,
And you're thinking only the multiplicative operator. Yes.
Where's like the finite energy field work? I know.
You mean like C mod N?
C mod, yeah.
Yes. So
That's it, I mean,
the only difference is the notation is written additively. All right. Can anybody pick out what the single generator is here? One term six. But he gave us a lot, you know, thanks for that infinitely many examples, right? There's a lot of them there. Are there any more? Wow. That's generated by the element 1. 1, 2, 3, 4, goes on forever. And you might say where the negatives come from, but remember, when you generate a group with something, not only do you use the element, but you're allowed to use its inverse as well. So that gives you the negative 1, negative 2.
maybe instead of angles on we're basing on a circle and you circle for angles stuff.
Well, I mean, it depends on which angles you're using, right? You can't use all of them in reals.
Let's say not basically the rationals or the integers, you know.
So is the rationals a cyclic group under,
Or probably integers, like 1 degree, 2 degree,
yes,
Or is C mod N, or is that C mod N?
right?
Or is that like by definition just additive or like multiplication? Oh, it's
No,
just,
this is just additive right here, and this one's additive too.
Okay.
Right, yes.
Oh, and when you, for that definition, very much another one, G, are we assuming G is a group? Already, or we're saying that,
Yes. Yes. Yes, we're assuming right out of the gate. Okay. Yes,
There are tools that has a generator in both the addition and multiplication.
so you're saying you have something that acts as a generator both additively and multiplicatively?
Not
Well, you need something that's co-prime to, in a field,
I was thinking.
well, if it's,
Or a ring.
but it's generator, well, no, because in the field, what'll happen is characteristic B, and additively it will go to 0 at B status, right, if you fill on it more often. So, that's it. That's all. So my example is kind of over. If you have any cyclic group on the planet, if it's finite, it is isomorphic to, you may write it differently, right? You might write the group something like. This group is written multiplicatively, but it's isomorphic to Z6, for instance. Fine. Any group that is cyclic is either infinite, in which case it's isomorphic to Z, or it's finite, in which case it's isomorphic to Z. This is really cool because it also shows that the real numbers, no way that ever a cyclic group.
Yeah.
It's too big.
It's
It's
too big.
uncountable. Right? So
That is true. Or
Direct diagonalization group.
well, I don't think of this. So if G is cyclic. Then G. Then by X. Then G is equal to set of X. Now, you all might say, well, Jim, what happens if G is cyclic? I'm sorry, what happens if G is finite? Notice this is the list of things in G. I did not say the list didn't repeat. Right, so it's possible that, for example, if you have that A6 example, this might go X is 0, which is the identity, X1, X2, X3, X4, X5, and then at X6 it goes back to the identity. I didn't say these are all different, but I'm saying that that's what the group is. Okay, so let's kind of get to this. Proposition. And this will go toward proving this wonderful result that we have here, but it's also some interesting observations. And how many of you thought it was a little weird that we define the order of a group to be the number of elements in the group? And then we define the order of this element to be the smallest n, such that x to the n is the identity, right? It seems like I had a little stroke there, right? There's total non sequitur. We're going to see as we go along that there is a connection. There's a reason why it's called that. So, proposition 323. If E is generated by X, so suppose I do have one of these cyclic groups that's generated by X, then your set G, that is the number of elements in it, is equal to the order of X. So that is a big part of the connection. the smallest n to which this is the identity is equal to three. I'm gonna take this apart in cases. Let me start by making a mark. Note that. In an n case. The order of x is less than or equal to the order of d, right? Because what's the order of x? It is the smallest power, positive power, that's the identity, right? So when you go through those powers, the identity x, x squared, whatever, every one of those elements has to be a distinct element of G, okay, right? So no surprises there. And of course, the group generated by x is a subgroup. You don't need anything about the group being cyclic here. This is true for any group. If you have an element X in a group, the order of that element is less than or equal to the order of G, whether it's cyclic or not. And the group generated by X is a subgroup. That is always.
That's the equal.
If the group G is cyclic and X is the generator, then you get equality. But you need both of those things to happen. So let's suppose first. That. Finite. And it's generated by X. It suffices in this case to show well, because if this is the case, then this remark gives you that the order of G is equal to the order of X. And that means the number of distinct elements in G is precisely equal to the order of X. And so, right, so that gets redundant for us. Since every power or every element of G is power of X. Okay. Consider set I. Okay, so every element we put out, in this case here, which is generated by X, every element of G is power of X. So I am going to consider the set of integers between 1 and n, where n is the order of X. And I'm going to consider the function I G given by f of little I is X to the I. This is surjection I Distinct elements. Because what happens to this, when you hit N, you go back to the identity, right? But and you start over again, but every element of G must have been covered, right? Because every element of G is power S. So order of I, the order of X, is greater than or equal to order of G, which is what we want to show. If G is of infinite order, and G is generated by X, then X cannot be X cannot be a finite order. Because everything in G is power of X, but if X has finite order, it only produces finite many things and starts over. Right? So that gives us the proposition we want. Okay, here's kind of one, and this is similar to one of the things you do in the homework for this week. And I'd also like to point out that this is why on homework 1, I put all the properties of the integers. This is one of the places it comes up. What G is root? Element of G and uh, uh, let me start over. Yeah. The idea. X, suppose X to the end is the idea. And you also know that X to the end is the idea. The idea is what nifty thing is.
X and minus M.
That is true, but can you get something even more straight about? Yeah, actually, I'll follow up a little further with what he said. He said, well, X in minus is the identity. That's certainly true. In fact, you go from the any linear combination, then it's the identity. Thanks to that top. What's your favorite linear combination? So if you know that, like, for example, X to the 4th is the identity and X to the 6th is the identity, then it must be the case that X squared is the identity of the past. So again, I'm going to proof of this because it shows the utility of how the integers, basic properties of the integers factor into this so much. Proof. And so there exists A, B, and the integers. With D. We actually proved that in the homework, right? X to the D. That's X to the A M plus the D N, which is X to the A M, X to the D N, which is X to the M, A, X to the N, D. Got that? That's both big. And there's. Okay. Any questions? So here's the classification. Statement. Uh. Zero. All right, so number one. Last one. Yeah. He is finite. The order of T is then G is isomorphic. And I write the fact that these are in the plus for kind of dramatic purposes here. Okay. Okay, so I'm gonna write G. I'm gonna prove one. Maybe I'll do two as an exercise because it follows very much from one. Or it's very similar in spirit. Okay, so first one, we have G is cyclic, and we're assuming that G is equal. Now I'm going to claim here that this is the case. I'm going to show this for here. Let me point out that X to the N. Not a big surprise, right? But I want to show the other way. If X in, so it's in, and this implies in. So yeah, so to this end, in, not M, N equals then without loss of generality. N is bigger than M. And by X to the N is X to the M plus K, some K in the natural numbers. Sorry. I'll write n equals m plus n. So x to the n was x to the m plus k. So x to the m, like this I can here. Therefore, x to the k is equal to the identity. So g is equal to 1x x to the k minus 1. And then piece. And it's nothing. And that's kind of going to do it for us because consider P from G into C given by P X N. Notice that P of X to the N times X to the N, P of X to the N plus M, which is N plus M, which is P of X to the N plus P of X to the N. So it's a homomorphism. Kernel, well, actually, because of the fact that I bothered to do that, if P of X to the N equals P of X to the M, then N equals M. So phi is 1 to 1, and phi is onto. It's pretty clearly onto because given any integer b, x to the b goes there. So G is isomorphous. And that's the proof of the infinite case. Yes, ma'am.
The bottom line on that side, where did we get that, x to the n? Oh, wait. Or yeah, how did we get that x to the mk equals x to the?
Are you okay with this?
Yes.
This is what you're bothered about? Because we're assuming that x to the n equals x to the m. So
Oh, okay.
other questions? All right, well, you have a good one, and we will see you folks at least by Wednesday.
Things I improved in the second homework, I think, earlier. I think I got like 22 instead, so we're doing better. It's still need to improve though, a lot.
Yeah.
I probably just need to chat and things, because this worked like great so far,
Don't worry.
So I guess the first one for what's hard.
Okay.
I guess smart emails is real on the curve score,
Well, that's right. You can email me or you can come on, something.
Okay.
I'll let the current one go now.
That's. But that's.
But unfortunately, you have to see me because Cambridge is.
Yeah,
Like, hard.
that's good to hear. Trying to improve, all groups,
Mhm.
Because it's gonna work a bit harder next time. A little smarter, that's right. Really just, hey, we're going through everything.
And I don't think they was.
They can put on my fridge. People always ask me this. What do register parents do for me? Well, they make it better for them. There's that philosophical. I don't know what they do, but so in a certain sense, yeah, they're doing it so this recipe. Right? I can't do anything. But what I do is, I mean, somebody that's miserable failing the course, not passing their credits. So what they do is sort of unexplainable, but it's an advantage. It's the last thing I look at before I write a software. So, yeah, I do everything, worry about the numbers, figure out what's last. So that's probably the biggest thing. And I just. Yes. That makes it so fun.
I didn't know that close, but here I've only waited. I've got. It's hard to, you know, this.